In section 3.7 we're going to be looking at the chain rule. Basically the chain rule allows us to take derivatives of a whole entire another set of functions that we haven't been able to work with before. Chain rules work specifically well for composite functions. For instance, we are used to taking the derivative of something like the derivative with respect to x of x squared plus 1 quantity squared by actually foiling this out. First outside, inside's last, and we're left with x to the fourth plus 2x squared plus 1. And then we take the derivative along our merry little way. The derivative of a constant is 0, and that's our solution. Well, what if, and that's pretty easy to do, so no complaints there, but what if we had something like the derivative with respect to x of x squared plus 1, let's say to the 100th. There's no way that we want to expand this out, multiply it out, FOIL it out, and then actually take the derivative. So our good old power rule doesn't really work well here. It works, but it's a lot of work. So what could we do to work with this? Well, this is actually a composite function. This is the function x squared plus 1 raised to 100. So I could have two functions, f of x, which is x squared plus 1, and I could have another function, g of x, is equal to, let's say, x to 100. Well, a composite function is when I plug one function into the other. So g of f of x would mean everywhere I see an x in my g function, I plug in the entire function of x. So this would be g of x squared plus 1, so that would mean I take this entire value and plug it in here, and I would get x squared plus 1 to 100. So this is a composite function. Well, how do I take the derivative of a composite function? I use the chain rule. So let's go ahead and look at what the rules for the chain rule are. Basically, what the chain rule says is to take the derivative of each component and multiply them together. So if you wanted to follow the book notation, f of g of x composited prime, they would say that's equal to f of g of x, meaning I take the derivative of f and plug g in, times the derivative of g prime of x. And that's a little bit complicated. When I think about the chain rule, I think about it a little bit differently. I look at the derivative with respect to x of some function of u. Now u is any expression of or a function of x. And to me this is equal to f prime of u times du dx. Okay, so you might think, well, that's no better than the one you just looked at. But I think this is a little bit easier to look at when we remember where u is a function of x. Now, the really super easy way to remember the chain rule is the derivative of the outside times the derivative of the inside. That's how the chain rule always works pretty nice. So another way you can think about that is outside prime, prime, inside prime. And the best way to kind of start working with these is to just go for some examples. So let's go ahead and look at some real basic examples, and then we'll also bring trig derivatives in, because that's where chain rule really shines, is when we're working with derivatives of trig functions when the argument of the trig function is something besides just a plain old x. So let's go ahead and start with the trig function. The derivative with respect to x of the sine of x cubed plus 1. Okay. Well, the derivative of the sine function means the kind of the outside piece. So here's the outside. Okay. So the derivative of the sine is cosine argument. Now I need the derivative of the sine of the argument. Now notice one thing that never, ever, 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 ever will change here is the argument of the trig function. Note over here the argument was x cubed plus 1. Note over here the argument is x cubed plus 1. Never, ever, ever change the argument of the trig function. Okay, that's a very, very common mistake to make, and we don't want to do that here. So we need to take the derivative of this next component. So we have the cosine of x cubed plus 1, and always put parentheses around the arguments of your trig functions. And then I have the derivative of x cubed plus 1, which is 3x squared. That's my derivative. However, we don't want to make the mistake of thinking, golly, I should multiply these together. So what we do is we pull any coefficients out front. So our derivative is going to look like 3x squared cosine x cubed plus 1. That's my derivative using the chain rule. Now again, it's not as obvious right now what the chain rule really is good at, with the trig function because talking about outside and inside derivatives, really didn't show up too closely here. So let's go ahead and look at another example where we're using the chain rule. Let's look at this one we had up here of the derivative of x squared plus 1 to 100. So let's look at the derivative of x, or the derivative of x squared plus 1 to the 100th with respect to x. Now, remember, we need the derivative of the outside. So what I do is I bring this 100 down, decrease the exponent by 1. That is the derivative of the outside. Now I need to take this times the derivative of the inside. So that's the derivative of x squared plus 1 because that's the inside component. So let's go ahead and keep writing. We have the derivative of the outside that we're dragging along. Now the derivative of the inside, the derivative of x squared is 2x, the derivative of 1 is 0. So that's my derivative. Of course, we're going to pull out and combine any coefficients that we can. So this derivative, f prime of x, is equal to 100 times 2x, which would be 200x, x squared plus 1 to the 99. X squared plus 1 to the 99. So, derivative of the outside, and then up here I had the derivative of the inside. And again, the chain rule is just fantastic. It opens up so many more opportunities for us to take derivatives. So let's go ahead and look at some more examples. Let's look at the derivative with respect to x of the square root of x cubed minus 2. Well, first of all, we want to rewrite this in exponential form, so this would be x cubed minus 2 to the 1/2. Now I can see I have an outside component and I have an inside component. So for the chain rule, the derivative of the outside, I'd bring the 1/2 down, decrease the exponent by 1, and then we multiply it by the derivative within. The derivative within would be the derivative of x cubed minus 2. So this piece right here is the derivative of the outside. So this is outside prime. This piece will be my inside prime as soon as I actually take that derivative. So simplifying, dragging along, the derivative of x cubed minus 2 is just 3x squared. The derivative of minus 2, derivative of a constant, is 0. So we can simplify this a little bit. Again, all the coefficients I need to go ahead and pull out front. And I get f prime of x is equal to 3x squared in my numerator. And then this flips because of the negative exponent, square root of x cubed minus 2. And this is my derivative. So again, the chain rule just is really slick in helping us to work with a lot of these different types of functions. Let's go ahead and look at a lot more trig derivatives just because they're so cool. Let's look at the sine of x squared. Let's take the derivative with respect to x of the sine of x squared. Okay, chain rule. The derivative of the outside times the derivative of the inside. The derivative of sine argument is cosine argument times argument prime. Okay, so that would be cosine of x squared. The derivative of x squared is 2x. And of course, we don't want to confuse multiplication with that argument, so let's go ahead and pull it out front. And I get y prime equals 2x cosine of x squared. Now, did the argument change? Nope, the argument stayed the same, and that will always be the case. So always keep your eye on that. A lot of people try and put the derivative as the new argument, but that's not what's going to happen here. The argument never changes. The derivative of the outside times the derivative of the inside. Let's go ahead and look at the derivative with respect to x of the cosine of the square root of 2x cubed plus 3. Well, rewrite it in exponential form. That's to the 1/2. Now we take the derivative of the outside. Now this one's a little bit complicated because you might be tempted to take this 1/2 out front of the cosine, but that's not the case. For a trig function, the outside means basically looking at the trig function unless the entire thing is squared. So in this case, the derivative of cosine is a negative sine argument. And remember, the argument never changes. So the derivative of the cosine of the argument is negative sine argument times argument prime. In the argument prime, I bring the 1/2 down. Actually, let's just write it out first, and then I'll actually take the derivative. So we'll have 2x cubed plus 3 to the 1/2. Okay, rewriting. Remember, the argument never changes with the trig function. Now I'll bring the 1/2 down, decrease this exponent by 1, and then I'll multiply it by the derivative within, which is going to be the derivative of 2x cubed, which is 6x squared. Okay, and then of course we want to rewrite and pull everything that we can out front. It looks like to me this half cancels here 3 times, so I have a 3x squared, and I have a negative value. So I have a negative 3x squared sine 2x cubed plus 3, and then this piece flips into the denominator, so that's going to be over the square root of 2x cubed plus 3. And that's my y prime, or f prime of x. That is my first derivative. Okay, let's go ahead and look at another trig derivative that involves the chain rule as well. Here let's look at the derivative with respect to x of cosine cubed of 4x. I think a good idea is to rewrite this, and let's understand cosine cubed means I'm cubing the cosine. I'm not cubing the argument, I'm cubing the cosine of the argument. So we would rewrite this as a cosine of 4x, and always put parentheses around the arguments of your trig function, cubed. Now I can see pretty clearly that this is a chain rule. This is the derivative of the outside times the derivative of the inside. Well, the outside part is just this function cubed. So the derivative of the outside, I'll bring the 3 down, decrease the exponent by 1. So bring the 3 down, decrease the exponent by 1. So here I have cubed. If I decrease cubed by 1, I get squared. And then I have to multiply it by the derivative within. So I need the derivative of the cosine of 4x. Now, holy cow, this is another chain. Because to take derivative of this piece right here, I'm going to have to use another chain rule. So this was outside prime. This is going to be inside prime. But in order to take the derivative of inside prime, I have to have another inside outside. So let's go ahead and write this out again. This is going to be 3 cosine of 4x quantity squared. The derivative of the cosine of 4x is going to be negative sine of 4x times the derivative of 4x. And of course the derivative of 4x is just 4. I guess I could pull this negative from here out front right now. Now notice, none of the arguments ever changed of my trig functions. No matter if I went from sine to cosine, etc., the arguments of the trig functions never change, and this is something that you can count on. The arguments of the trig functions will not change. Now here the derivative of 4x is 4. And go ahead and pull everything out front. I have a negative 12 cosine squared 4x sine of 4x. And that is my f prime of x, or my derivative. So these can get pretty involved, but again, a lot of times they're much simpler than we could have used with the power rule, and sometimes I couldn't have worked the problem at all without it. So it's essential that I have the way to take a derivative of a composite function. Let's go ahead and look at another example. These are fun. The derivative with respect to x of the cosine of x squared plus 1 to the 4th. Now how is this different than the one we just worked? Well, the one we just worked, I was cubing the cosine, so I could rewrite it as the entire function cubed. Down here, I'm taking the argument to the 4th power. This does not need rewritten. So in this case, when I take my derivative, the derivative of the outside piece would be the derivative of cosine. The derivative of the cosine is a negative sine of the argument. And remember, the argument does not ever change, times the derivative of the argument. Okay, and the way we're going to start explaining this is we're going to start calling this u, and pretty soon we'll start saying, the derivative of the cosine of u, where u is any function of x, is equal to negative sine of u prime, which means the derivative of u. And you can see that that's actually what we're up to. So rewriting here, the derivative with respect to x, I bring the 4 down, decrease the exponent by 1, and then I have another chain back, times the derivative of x squared plus 1, which is 2x. So one of the reasons I call it the chain rule is because I can have a really complicated expression and it just keeps linking back. So let's go ahead and write this in simplified form. 2x times 4 would be 8x, and I have a negative out front. So I have a negative 8x Let me see here. Sine x squared plus 1 to the fourth times x squared plus 1 cubed. But you know what? We might misunderstand this and try and multiply these. So let's go ahead and pull that clear out front. So this is negative 8x quantity x squared plus 1 cubed sine x squared plus 1 to the fourth. Now this is y prime, my first derivative, the slope of the tangent line. If my original function was position, this is velocity. And now it's pretty clear that I do not combine anything with this argument. But again, the argument of my trig function never changed. From cosine to sine, my argument never changed. And that's really important to remember because a lot of people make that mistake as they change the argument of the trig function. Let's go ahead and look at another example. Let's look at the derivative with respect to x of the tangent of x over x plus 1. Okay, well, the derivative in general, the derivative of tangent argument, tangent u, is secant squared of u prime. Okay, and again, those are kind of our shortcuts. If the argument is anything other than x, I need to remember the derivative of the tangent u is secant squared u prime, the derivative of u. U is any expression of x. So if we were to write out this derivative, the derivative of tangent, which is the derivative of the outside, would be secant squared argument. And another way to write this is argument prime. So some people will write it as argument prime, as long as it doesn't look like a 1. Now what we've been writing is secant squared argument times the derivative of the argument. They mean the same thing. It's just another way to notate the same thing. It's kind of whatever you like best. But interestingly enough, the derivative of this piece is going to be the quotient rule. So that's going to be a little extra work. So secant squared of x over x plus 1. Now I need the derivative of x over x plus 1. So now I start with the quotient rule. So I start with the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Of course, I can simplify the heck out of this thing. I'm going to go ahead and pull this all out front. I'm left with x plus 1 minus x, which just leaves me with 1 over x plus 1 quantity squared times this entire secant squared x over x plus 1. And this is my derivative. This is the slope of the tangent line at any point along the graph. Now, what about the argument? Did it change? Let's go up here. The argument up here was x over x plus 1. The argument here is x over x plus 1. So the argument never changes. When I take the derivative of a function and eventually when I integrate a function, the argument of that function will not change, and it's so important to remember that. It'll really make your life a lot easier and you'll make fewer mistakes if you can keep that one remembered. So again, first derivative. And of course we could take the second derivative. Let's go ahead and look at another example. In this example, we're going to have quite a bit to keep track of. We're looking at the derivative with respect to x of the square root of x squared plus square root 3x minus 2. My recommendation is get rid of all the radicals and rewrite them in exponential form. So this would be 3x minus 2 to the 1/2, all to the 1/2. Now we can see what we definitely have an outside and inside. Derivative of the outside, I'd bring the 1/2 down. The derivative of the inside, I'm going to have another chain rule. So let's go ahead and start on that outside piece. I'd bring the 1/2 down, decrease the exponent by 1. Now I need to multiply it by the derivative within. So I'm taking the derivative of x squared plus 3x minus 2 to the 1/2. So dragging all this bit along, because here that I'm writing in blue is the derivative of the outside. Now when I take the derivative of the inside, the derivative of x squared is 2x, and then the derivative of this piece is yet another chain rule. So I need to take the derivative of the outside times the derivative of the inside. I bring the 1/2 down, decrease the exponent by 1, and multiply it by the derivative of 3x minus 2, which is 3x. And of course this can be cleaned up quite a bit. So here let's go ahead and keep on simplifying. When we have this component, this entire value will flip, This is going to look a little bit funny. I have the square root of all of this. Square root of 3x minus 2. That's this first piece. And then for this second piece, I'll have my 2x plus the 3x stays up top. The 2 was already in the denominator, and then I have root 3x minus 2. And again, this is f prime of x, or y prime. It's my derivative. And there is some simplifying that could be done here, but I think it would get pretty ugly pretty fast. But that is my derivative. This next example is a little bit more of an application problem. So for this example, we have the equation P equals cap RI squared. P is power, R is resistance, I is current. We want to find the derivative of power with respect to, in this particular case, T. Okay, we can assume T is time here. We don't have that given to us as our variable yet. And then we have certain parameters. R is equal to 1,000 and I is equal to sine of 4 pi t. You might come up here and say, well, there is no t to take the derivative with respect to. But as soon as I plug in sine equal 4 pi t, I will. So that's the first thing that we're going to want to do, is we'll plug in. P is equal to cap R I squared. So that's going to look at the sine of 4 pi t quantity squared. Now remember, it's not the argument that's being squared here, it's the entire sine function. So here, I need to keep track of what's variable and what's constant. Now one thing that we could do also is in place of this r, we could record the 1,000. So we could look at P equals 1,000 sine 4 pi t quantity squared. Well, this one's going to be pretty easy then. The derivative of power with respect to time. The 1,000 is already here, so when I bring the 2 down, they're multiplied together. Then I decrease the exponent by 1. So that's going to give me a 1 here. And then I take the derivative of the sine of u, which gives me the cosine of u, which in this case is just whatever the argument is, times the argument prime. The derivative of 4 pi t is just 4 pi. And then of course we can simplify from here. It looks like we have quite a bit we can pull out front. I have 2,000 times 4 pi would be 8,000 pi. Sine 4 pi t, cosine 4 pi t. Okay, and so that would be the derivative of power with respect to time given those particular parameters. The very last example that I'd like to look at here is I would look at given y, given a particular function y, is equal to cosine of 4x cubed, I would like to find y double prime, which means the second derivative. Well, to find the second derivative, the first thing we have to do is find the first derivative. So the derivative of the cosine of u is negative sine of u prime. Now notice what didn't change here. The arguments of the function did not change. And again, we're going to pull our coefficients out front, and we're left with y prime equals negative 12x squared sine of 4x cubed. So there is my first derivative. Now to find my second derivative, I'll have to apply the product rule. So these can get pretty involved. Now the product rule is the first function times the derivative of the second function plus the second function times the derivative of the first function. So there's our setup. Let's just go ahead and take that derivative now. And again, this is y double prime. The derivative of the second function would be the derivative of the sine of u would be cosine of argument times the derivative of the argument. The derivative of 4x cubed is 12x squared. Okay, the derivative of a negative 12x squared in this particular case is going to be negative 24x. Now, these are coefficients. Pull them out front. This is a coefficient. Let's pull it out front. So I get y double prime is equal to 12 times 12 is 144, and that's negated. X to the fourth cosine of 4x cubed minus 24x sine of 4x cubed. And there's some simplifications that we can do here. We can pull out at least a factor of 12. It looks like we can pull out an x, but this is my first derivative. slope of the tangent line at anywhere along the graph. The last thing I'd like to do is to kind of summarize the derivatives of trig functions as it involves the chain rule. So I'd like to summarize trig function derivatives. Now before we were working with trig function derivatives, we were only working with functions that had an argument of x. Now I'd like to look at functions that have some generic argument of u. And again, u is any expression that involves x. So it could be a binomial, it could be a trinomial, it could be a radical. Okay, so the derivative of the sine of u is the cosine of u, u prime. The derivative of the cosine of u is negative the sine of u, u prime. The derivative of tangent u is secant squared of u, u prime. Now this u prime that we keep talking about does not combine with the argument of the trig function. Okay, so this is exactly not combining. We can pull that out front. Notice what doesn't change. The argument doesn't change between the u in our original function and the u in the derivative. So that's something we need to look for. Let's go ahead and look at this in terms of the cosine of u, the cotangent of u, and the cosecant of u. Now remember, with our cosine, cotangent, cosecant, the derivative is always negative. So that's kind of how I remember those. The derivative of the cosine of u is negative sine of u, u prime. The derivative of the cotangent u is negative cosecant squared of u, u prime. And the derivative of cosecant of u is negative cosecant u, cotangent u, u prime. Notice there's not two u primes to go with each of the arguments. It's just one u prime overall. We will definitely want to memorize these. Definitely memorize these. So now you have a whole other set of functions that you can take the derivative with respect to. You should be able to do a lot more types of problems, and they can get pretty involved, but the thing to remember is to stick with them.